Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm going to be trying to diagnose and repair this IBM 5160 motherboard. It first appeared on a second channel video where I took apart a derelict IBM 5160 that had been donated to me, and it worked for a little while, but then it just stopped working. I have a little bit of notes on here, so it might help me with troubleshooting, but I have no idea what's actually wrong with this. So without further ado, let's get right to it. All right, so this is the motherboard. I wrote IBM 5160, bad RAM at U63, fixed. Now no post, stack error question mark, bank 0, I put a question mark. These are just guesses. Now what I'm talking about with stack error is while the machine was running, all of a sudden it just said stack error. And then when I power cycled it, it no longer worked again. And you can see here, one of these RAM chips is not like the other, and this is the one right here at U63. That was the one that was bad originally, and I swapped it out. This thing has 256K on board, so these are banks of 64K each. And from my recollection, as the note says, it just stopped working, and that was that. Now, we have a couple good things going for us. There's no custom chips, at least I don't think there's any custom chips on this board. Oh, actually, this thing here looks custom. This chip dated 1984 says D8288. All right, well actually this is the equivalent of the Intel 8288, which obviously is part of the regular chipset that makes up the original PC XT, the 5150 and the XT. It looks like this IC just makes up some of the signals that run the bus and the various components on the PC. So that's something that I can definitely still find. In fact, I might even have a spare. Right next to the CPU here is the Intel 8284, and this also has some function, which I can't remember what it is, but it has something to do with the PC architecture. But also that chip is still something you can find. It's not some ultra rare part. And that's what I'm really talking about. It looks like every single component on this motherboard are standard off-the-shelf parts, meaning if anything on here is bad, we can actually find a replacement for it. The issue of chips that can't be replaced is more of a problem on later machines because they combine like a bunch of this logic here, for instance, into a single PAL chip, PAL or GAL, programmable array logic. And the issue is those chips can't often be copied or read out. So if that chip goes bad, and if you can't find a replacement, you're dead in the water and the motherboard is toast. Motherboards like the Macintosh 128 and 512 and even the Mac Plus look like they all have standard ICs on them. But the issue is Apple did use programmable array logic and the equations for those have never been released. So if one of those chips goes bad, if you can't source a replacement off another of the same motherboard, the motherboard you have is now a paperweight. You may have noticed I've been wondering about this IC socket right here. I'm pretty sure that this is supposed to be empty. There's a little bit of dust on that socket, which implies that it's been empty like that the entire time this board has existed. And I just did a very quick Google search for IBM 5160 motherboard, and here is one right there that has that exact same IC socket unpopulated. And if you look at the top side of this board, it doesn't look like any of these traces actually connect to the socket. Like this trace here comes out on that side. So these just run straight through. And this is the socket on the back of the board. It has one trace connected. Now I think there's a ground plane inside this motherboard, potentially a 5-volt power plane as well. So those might be hooked up to this IC. But I do have to wonder what this chip socket is for. If anyone is familiar with what U84 does, yeah, please let me know in the comment section below. Okay, time for a little troubleshooting. I've just connected a speaker in the power supply. Let's see if we hear a beep when I turn this on. All right, there was no beep. The power supply was actually shorted out. So I think at the minimum, we have a bad tantalum on this board here, probably on the 12-volt rail. So if you look at the power connector here, the yellow wire is the 12-volt rail. The red wires are 5 volts, and I forgot what the blue, white, and the orange do, but one of them is like power good, and I think there's a -5 and maybe a -12 on this power supply. So we're going to be going from this pin right here, which is the third from the keyboard connector, and then to these middle pins for ground. All right, and I'm using the virtual bench, so if I short these together, there's no beep, but we're getting 0.3 ohms. Oh, actually, there is a continuity feature on here. Let me try this. Oh yeah. All right, it actually beeps from the PC speaker. Well, you know, the sound card. That's handy. Okay, so to not annoy everyone, I'm gonna null these out. So I'm holding the probes together. I'll squish them as hard as I can and I hit null offset. There we go. So that just zeroes out the resistance measurement just so we get a little bit more accurate of a reading. All right, so let's just test. So there's the resistance from ground to ground. So 0.32 ohms, whatever. Nothing, nothing, nothing. Okay, that's a ground. All right, so to this blue one, nothing. 12 volts, nothing. Okay, wait a second. None of these are shorted. That doesn't make sense. Okay, 5-volt rail, we're getting 62 ohms. That's definitely low-ish, but that's not a dead short, and there's a lot of 5-volt stuff on this motherboard. So, okay, I'm going to switch this over to DC, and I'm going to leave this in the 5-volt pins there. Let's turn this on. Okay, I don't know what happened the first time. The fan was not running on this power supply. We're also getting no beep, so I'm just confirming that it's working exactly like it was before. So we're getting 11.85 volts on the 12-volt rail, 5 volts on the orange wire. That must be power good, minus 11.8, so that's a negative rail, and the white wire must be minus 5. Yep, there it is, minus 4.77 volts. All right, so I'm just going to power cycle this again. Definitely no beeping. Now I'm going to give it the old feel test. I'm going to look for chips that are very hot. So far, so good. Now, if you have a thermal camera, of course, you can use that to help you troubleshoot. And keep in mind that some of these ICs, like these Intel ones here, they probably get relatively warm as it is. They're ceramic packages. So far, everything feels fine. Nothing is super hot. All right, so nothing obviously is burning up. I'm going to plug in this postcard. Now, the postcard, unfortunately, will not have anything to display on the numeric display. That first showed up on the IBM AT5170. So on a machine like this, all this is going to do is show us the voltage rails. That's this set of LEDs here on the left. And on the right, we have clock, I/O ready, frame, and reset signals. So I'm going to hold the motherboard like this, and let's turn it on. All right, so the way the LEDs look there is normal. I'm going to power cycle it just so you can see what it looks like. What I'm looking for is that the reset line, which is this LED right here, closest to this little speaker, should be on for a second and then turn off. That's going to indicate that the CPU is in reset, and then the reset circuit releases the CPU and allows the machine to boot. And you see that? It was on for a second and then went out, and then when it went out, this LED down here came on. So this machine is definitely trying to boot. It just isn't. Now, I have definitely shown this postcard a lot on the channel. You can buy these from eBay or from Amazon. They're very inexpensive. And if you're working on PCs and doing any troubleshooting, I highly recommend it. Of course, it's got a PCI connector here and an ISA connector, so you can do both with this same card. You might be wondering why I put tape on here, and that's because this LED display was showing the current postcode, and this one was showing the previous code. So if this showed like a 2, this would just show a 1 as it counted through the post, which sometimes can be helpful for troubleshooting to see what the postcode was right before the one it got stuck on. Personally, I found it distracting that there were 2, so I just put tape over the second one. This wire here also is for a speaker that's integrated into this board, so you can connect this up to the speaker connector, and if you want to hear beep codes, it may be a very convenient way to do so. I have the virtual bench up on the screen, and alongside I have the pinout for this DRAM right here. What I'm going to do is quickly probe the D pin, or pin 2, on the DRAM, especially on this row here, which is bank 0, the first part of memory. And that all goes back to the fact that when the machine died, it had a stack error. And I'd imagine on the PC, the stack is stored in the lowest part of memory, which would be this first bank. And almost certainly, a PC won't boot without its first bank of memory. On later PCs, it will actually give you beep codes if that RAM is not working. Like if you have no RAM. I just don't know on the 5160 if that's the case. Oh, you know what? I should go Google what the beep codes are for it. Looking at -0degrees.net, there's not a lot going on with beep codes. There are some beep codes. Continuous beep is like a faulty motherboard, or one long beep too short is some switch configuration errors. Well, I didn't touch those, so I know that's not a problem. or 1 long and 3 short is you have an EGA card, okay, whatever. And everything else down here is stuff displayed on the monitor, which we're not getting. And when you get nothing, it says this symptom has many causes. All right, so we'll get back to that in a second. All right, so I've powered this up, and let's take a look at pin 2 on all of these sockets. All right, we see activity. All right, so the first chip, there is the waveform, and you can ignore that ringing you see at the bottom. That's just because of the ground lead I have here. It's not ideal for probing this speed of a signal. If I turn this off, turn it back on, you get some activity there. Look at that, and then it dies. So the machine is running. Let's just quickly check the other lines here. Okay, so this doesn't look good. Let's turn this off and back on again. Something is weird there. Do you see that signal that we saw briefly there that was like half height? That right there, that's not right. Something's wrong on that data bus line. How about this one? Oh, this one looks screwy too. When I power this on, it should look like this first one here. See that? Nothing is half height. It's either all full, up at 5 volts, or down by ground. Let's check this one. That one looks bad too. This one as well. What's happening exactly here? No, bad. That's no good. And the virtual bench just went offline. This happens sometimes when I'm toggling AC devices off and on, like this power supply on the bench here, and I have to actually unplug the power from the virtual bench and plug it back in from the back in order to get it to come back to life. It's a weird issue with this particular device. All right, and we're back. Okay, so I realize now that I don't even need to power cycle this. Like this chip here, it's doing that half height thing. This one as well. Yep. That's bad. That's bad. That is bad. These are all bad. Okay. Now you might be wondering why it's not doing it on this first chip. I have a feeling this is a parity chip. So 1, 2, 3, 4, 5, 6, 7, 8. That's probably 8 bits. And this one is probably used for parity. So it's not hooked up to the data bus in the same way as all of the rest. So unfortunately, I think the fault in this motherboard is not as simple as just a bad RAM chip in bank 0 here. I think something else has gone wrong that's causing a bus conflict, which is most certainly why we're getting that weird half-height voltage thing on the data bus. Okay, so I have the CPU pinout up here, and I want to check the data bus lines on the CPU. Now, one thing about the Intel 8088, which is different, of course, from, say, a 6502, is that it doesn't have separate address lines from data bus lines. They are multiplexed. So these pins right here are both the address lines and the data bus lines, and the CPU alternates between the two. And that's actually one of the reasons why the 8088 is not as efficient at the same clock speed as a 6502. And that's because those pins are doing that double duty. There are latch chips on the motherboard that latch those signals in. So when it's sending the data bus signals out, the latch holds those in place and then can send to the rest of the board. And the same for the address lines. 6502 has discrete pins for address and data. So it takes advantage of every clock cycle to send address signals and data bus signals out, or in, of course, both directions. So I'm expecting when I probe the address lines on here, the ones that aren't multiplexed, we should just see a nice clear square wave signal. And here we are on address line 14, and it all looks great. Here we are on the clock signal, and all looks good. And here we are on one of the address/data bus lines, and it seems okay. Let me stop it here. So, you know, you have stuff that's up here, and then things are a little bit lower, but that's still within TTL range. This would be 5 volts, 4 volts. That's okay. If it was down here around 3, 3.5, that's where you get into the nebulous land. Like on the RAM, if I stop this, we're at like 1.3 volts here. That is just not right for TTL signaling. So let's take a look at the technical reference for this motherboard to see what exactly is in between the CPU and the RAM when it comes to the data bus signals. Okay, so we're on page 28. And here's the main processor right here. Right here are the address buffers for A8 through 19. And remember, that's because those are not multiplexed. So you have standard 74LS244s. and then you have AD0 through 7, and those are the address buffers that get latched to be combined with the other A8 through 19 that can generate all of the address lines needed by the system to address 1 megabyte of address space. And next up is the 74LS245. It's a bidirectional bus transceiver, and that's what connects the multiplexed AD0 through 7 to the data bus lines. Now, if we follow that line over, it's to the next page. I think it's this one right here. There's another set of data buffers. Oh, and there's some more buffers here that go to the memory. So the memory is actually buffered twice through 2 sets or 2 74LS245s. It's actually interesting that this chip is here because when we were checking the signaling on the RAM chips, we were looking at this side of the signaling right here. Well, what could be causing those weird TTL signals to not be 5 volts or 0? It can only be the RAM. And it's very unlikely that all of this memory is bad. It's got to be either that 74LS245 is doing something weird or it's bad, or the chip select or the select logic for the RAM, which is this stuff right here, is somehow screwed up. And maybe it's selecting multiple banks at the same time. One way I can try to validate that is I could just remove these 3 banks of memory, just leaving this one single bank. Each one of these chips here is talking to this 74LS245 on individual data lines, 0 through 7. And when you look here at the layout on the motherboard, each data line on each one of these chips is paralleled to the 3 chips below it. So these 4 ICs, pin 2 is all connected. But normally the select logic would only select one bank of chips at a time. You wouldn't have multiple banks talking simultaneously. So here's a good test to see if the issue is selection logic. I'm just going to remove these 3 chips so that the only chip that's connected between here and this memory buffer is this one right here. That means that only one thing could be talking on the bus at a time, and you can't be having issues with multiple ICs trying to talk at the same time. And here's what I'm talking about for clarity. Imagine this chip here is trying to send a 1 to the data bus, that's 5 volts. And these 3 chips here are trying to send a 0. If they're all selected simultaneously, they're gonna fight each other, and you're gonna get something on the data bus that's not 5 and it's not 0. When RAM chips are not instructed through the RAS and the CAS signaling to be driving the data bus, they are ultimately the same as being disconnected from the data bus entirely. So the one chip that is connected and trying to drive the bus is not going to be fighting with the other chips. Let's take a look at pin 2. Okay, we're still getting it. Look at that. Did you see that? We're still getting that half height thing, which helps eliminate that it's not this memory control logic. In addition, this 74LS245 is bidirectional, so it has a signal that tells it which direction the signal is going. If that control line is bad as well, that could be a problem. So we're gonna have to go look in the schematics further down to see what controls this IC. All right, on page 62, we see the RAM here, and MD0 through 7, and that's memory data bus 0 through 7. That's the bus lines we've been looking at. Pin 2, it's also hooked up to pin 14. That's where we've been seeing these weird signals. You'll notice here MD0 through 7, it also comes down here, goes to this other bank of memory. It is also connected right here to U20, which is this IC here, 74LS280. This must have something to do with the parity memory checking. So I'm just gonna put a dot on that IC because that could be one of the problems right there as well. And if we follow this down here, it goes to sheet 7. Let's take a look at that to see where the memory data bus goes. MD0 through 7, it's probably just going to the other 2 banks of memory. So there's 1 bank and 2 banks. Yeah, okay. Okay, so here we go. There's the LS280, so that could be an issue. And if we scroll over here, right here is the LS245 U9, which is this IC right here next to these slots. It's a Fairchild LS245. So that could be a problem. Now right here are 2 signals that control this. There's the DIR pin 1, that's direction, and then the Q, which is the enable signal. When it is low, it actually enables this IC. So this is the direction pin 1, and that controls which direction the signals flow through this IC, whether you're reading or writing to RAM. All right, so you see some normal looking activity there on the direction signal. So now I'm on the enable pin for this IC, and there we go. We see normal activity on it, and there it just goes low, but I think the computer is just completely crashed or frozen right now. Let's check pin 2 on the RAM. Yeah, it seems like it's just sort of dead in the water. Back on the schematics here, the enable pin, let's see, scrolls down. It comes from RAM address select, which sort of has some other logic there. And the direction pin comes from X memory read write. Now, I don't know if logically those signals are working correctly. The direction signal is controlled by this 74LS74 here. It's not an impossible failure to have an LS245 that actually keeps the data lines connected even when it's not enabled. So I think what I'm going to do is grab a second oscilloscope probe and I'm going to check the enable pin on the 245 against what we're seeing on the data bus lines to the RAM chips. Because when the LS245 is not enabled, we shouldn't see anything happening on the RAM at all. And unfortunately, this chip is not in a socket, so I can't just pop it out and replace it to see if that is causing the problem. Okay, we have two traces. The yellow trace is the enable line for the 245, and then the red trace is on the data bus on pin 2 right here. So let's turn this on. All right, so it ends up in this state here where it's completely enabled all the time. I think the machine is just sort of dead. Let's turn this off and on. I'm gonna have to hit stop when all this is running here. So it is stopped right now. Let's turn this off and take a look at what we're seeing. So remember, the yellow trace on the top is the enable signal for the bus transceiver. So that chip is only turned on when this signal is low, which is right here. And looking at the waveform, I don't really see a lot of rhyme or reason. This address line was high at that point and the chip was off. Now that doesn't mean that the RAM wasn't trying to actually drive the bus, because it can still be selected. It's just when that chip is turned off, the RAM is driving the bus, but it's not doing anything. It's not connected to anything. What I'm going to do next is I'm going to pop out this RAM chip right here. So nothing can drive the bus except for the LS245. And then the only other thing that's connected is this 74LS280 chip here. And I don't think that chip is supposed to drive the bus at all. I'd have to look at the data sheet, but I'm pretty sure these are inputs only. And then it outputs either even or odd, which is how it calculates the parity. So this is the data sheet for that 74LS280. It's an odd even parity generator / checker. And here's the function table. And it does show that these are all inputs A through I, and it has two outputs here, even and odd. So with that said, let's turn this back on and let's take a look at what we see here. This right here is absolutely telling us that one of these two chips is faulty. And I have to say, I'm actually kind of leaning to this 280 chip, but it still could be the LS245. When the LS245 gets turned on, it seems to draw this data line all the way down to 0. And then the LS245 is turned off here and here, and then something is obviously driving the bus. Now, I haven't mentioned this, and I don't think I saw this in the schematics yet, but there could be something pulling up those data bus lines to 5 volts. That's totally possible. It's not always the case, but it might have pull-up resistors. So let's go check that out. No, I don't think there's any pull-up resistors there because it's not on this sheet. And MD5, the MD lines come up here and they just go straight to that. And there's no pull-ups. Pull-ups would be shown on these schematics if they were there. They would look like this. There's a pull-up resistor right there. That's pulling up through 4.7K to 5 volts on whatever line this is. You know what? I just had a thought that I might have been going down the wrong path the whole time here. I talked about earlier that there were no pull-up resistors on the bus here. Well, the thing is, that could be throwing me for a loop, and I should have realized this sooner. When you don't have a pull-up resistor on the bus, when nothing is driving the bus, it just kind of floats there. And that means that ICs that are connected to it can potentially drive the bus to weird levels. It's not necessarily just going to be 0 volts, but there is so little current driving the bus that it doesn't really matter. And as soon as you try to drive that bus, either high or low, there's no problem because you're only fighting against a tiny amount of current that was holding it like in the middle there somewhere. Maybe that's what's actually going on here. So I think I'm gonna grab a resistor, like a 10K resistor, and I'm gonna pull up that data line up to 5 volts, and let's see what happens exactly. So there it is. I stuck a resistor between 5 volts and pin 2, which should pull it up with 10K. And let's take a look at how this looks once I power this board up. ultimately, if everything is working, we should only see 5 volts or we should only see 0 volts on this line now. I hooked up the oscilloscope to the enable pin so we can take a look at how that looks. Okay, let's pause this. All right, so we see an enable and it drives the data bus to 0. And then we see another enable, but doesn't really do anything with the data bus, right? It's still sort of slowly rising up to 5 volts. We are definitely not seeing anything strange on the data bus anymore, right? There's none of that weird half and half 5 volt stuff. So I'm gonna say that weird 2.5 volt thing we were seeing was normal. And it just had to do with the bus floating, and it's not a problem at all. Now I'm used to fixing Commodore 64, so I'm used to looking at the way the bus looks there. I've never worked on a 5160 motherboard before, so this is a bit of a new territory for me. So you're learning with me here. This is a normal process. What's probably happening here with these two enables to the 245 is the first one is trying to write to the RAM chips. It's trying to drive a 0 into this particular RAM chip. And then probably what happens is the CPU attempts to read from it, which is what's happening right here. If the RAM chip were in place, we'd see a 0, and then we'd see what the RAM chip driving the bus to ground right here as another 0. So the RAM chip's not installed, so there's nothing to read back except for 5 volts, or it's raising up to 5 volts, and that is normal. And when I zoom out, everything looks normal. It's either pulled up to 5 volts or it's driven to 0, probably from the CPU. Now, there's still a possibility that everything's working perfectly, and it is the bank 0 RAM that's the problem. I kind of went directly down the possibility that there's a problem with the logic chips without just thinking that everything's actually working perfectly. Like, this is normal what we're looking at, and it's just the RAM that's bad. So before I go desoldering any chips, I'm just gonna quickly pull out some of these RAM chips here and stick them in bank 0, and let's see if that has any effect at all. All right, these RAM chips have been removed. I put them up above there, and I took these and I stuck them in bank 0. So let's just see if this actually works now. Now the speaker is hooked up, but I don't have a video card hooked up. Let's just take a look at what the activity is on one of these RAM chips. I'm gonna go out on a limb and say this machine is still dead as a doornail. We turn it on, let's see. Yeah, we see some activity, and then it all just sort of goes nowhere. What's interesting is with bank 0 in there, when I turn it on, it does seem to do quite a lot more before it kind of goes bad. See all this activity there? So I am still thinking that there's probably nothing wrong with these two ICs, and the problem is something else on the board. I mean, total red herring in the wrong direction for me. So I think the next step is to try some of the diagnostic ROMs that are available for the 5160, and there are two listed here on -0 degrees. There's the Landmark Diagnostic ROM, and then Rudd also created his own. Let's try this one, which I think is pretty old and been around for a long time. Click here for the ROM image. All right, we have this motherboard, and it requires a single 27256 EPROM, and it goes into U18. So there it is, there's the bin file. Let's use the MiniPro. Sometimes with these old chips and the MiniPro, programming it a couple times probably makes it work, can make it work a little bit more reliably. And yes, you can program an EPROM with the exact same image multiple times, and it just can sometimes reinforce the data that's stored in the chip. U18 is this IC right here. This is the BIOS chip, in with our diagnostic chip. It has to check the dip switches are set correctly for the correct banks of memory. Let's just go to on and on, which is only 256K, the first bank here. All right, let's turn it on, see what happens. Oh, it's beeping, that's a good sign. All right, so it says to check the manual for the beep codes. All right, so the beep codes are here. So there are high-low tones. We have up to 6 of those, and then you have short tones up to, looks like 9 of those. Okay, so that was 5 and 9, which is simply cannot initialize the monitor. I hope that basically the whole problem wasn't that I didn't have a video card in it the whole time. What? Let's plug a card in and see what happens. Here's a CGA card, which it says this thing works the best with. Unfortunately, my capture device here is not working, and it's not the capture device, the Elgato, it's actually my lab computer up here. The USB 3 ports have quit working on that thing, and they're on board the motherboard, and there are no more slots on that thing, so I have to buy a new computer for the lab. So I'm gonna be hooking up the HDMI, the RGB to HDMI to the monitor here. So unfortunately, you're only gonna be able to see what's on the screen through this device here. Okay, video card is hooked up. Let's see what we see. Oh, hey, look at that. It is running Diagnostics. Let me move the camera. All right, hopefully that's working. So wait a second, everything is working. Was this just a memory problem the whole time? Obviously that's a video card test, okay. Keyboard controller, what? I'm wondering if the keyboard failed because I don't have a keyboard plugged into the computer. I should plug one in and I guess run this test again. It just really seemed, looking at the oscilloscope, after I changed the RAM around, when I still had the stock BIOS in there, it just sort of stopped doing anything. And the speaker was hooked up. I was assuming it would beep if the video card weren't installed. Maybe not. Well, okay, I'm gonna swap back to the original BIOS because it looks like everything is passing. Obviously the floppy stuff will fail. Original BIOS back in. And yeah, about a minute later, nothing, no signal out of the CGA card at all. I'm gonna quickly go over all the switch settings here just to make sure everything is right. All right, well, let's try this again. No, it's definitely not coming up here, even set to CGA. Could there be a problem with the ROM BIOS? I mean, that is possible. I popped the chip out here, just checking that the pins aren't bent, and they are not. And that is definitely the IBM BIOS chip there. I'm gonna put back in this diagnostic ROM here, and then just let this thing run through its tests. There it goes. Let me unplug the speaker. Okay, it's unplugged. All right, I am back from dinner, and I have just left this thing running. It looks like it's passes 43. Everything on this side looks fine, although slow refresh has one failure, although it passed on the last time. But okay, I was just about to talk about the next error. Here's the error that is suspect. System BIOS failed right here. Now, I just assumed early on that this failure had to do with the fact that I replaced the BIOS with the diagnostic one. But over here, U33 Super Soft ROM checksum passed. So this is something else potentially. Over here to -0 degrees, I think this is the key thing. The ROM does not require the IBM ROM in socket U19 to be present. However, if not present, expect U28 system BIOS to fail. That is the one that was failing. So I've grabbed a fresh blank EPROM here, and I'm just double checking that it is blank, and it is. And these are the BIOS files that I downloaded from -0 degrees, and there's a README file right here. U19 is the IBM part number 5 and a whole bunch of zeros 27, which matches the chip on the motherboard right here. And that is 8K in size. They have included a version of this file here, which works on a 27256, and the image is repeated 4 times so that it can work in a 27256. Awesome. So I'm just gonna load up that file. Let's program this chip. Out with the chip that's potentially bad, maybe, maybe not, we'll see. Out with the diagnostic ROM, and I'll put back in the stock ROM that goes into U18. All right, what's gonna happen? Look, it's freaking working. It's actually working. It's booting the computer and everything. Look. This chip failed! Failed! I can't even believe it. That is one working IBM PC 5160 motherboard. Wow. I may as well put back all the RAM on this board that I was accusing of being bad. I have to apologize to the RAM. Like, if it had feelings, its feelings might be hurt because I accused it of being bad and causing a problem. And then these chips, I'm sorry, you never had a fault. I'm very glad I didn't desolder them. That would have been unnecessary and potentially damaging to this motherboard. And I'm just going to change switches 3 and 4 to off. That enables all 256K of RAM. Plug the speaker in. And here we go. Oh, we're only getting 192K. You probably couldn't even see that. 192K of RAM implies we're getting 3 banks of memory working, and the 4th is malfunctioning. So I might as well pop this XT diagnostic back into this motherboard. Let's see what it says about the bad memory. There it is, bit number 1. It's saying there is a problem. So we know right off the bat that that failed bit is in this 3rd bank. So I'm gonna go investigate that. Over to the schematics here to figure out exactly which is bit number 1. Here it is, MD1 goes to U32, U47, down to the next page, it goes to U60, and U77, so that one should be the chip. Well, I see the issue. Do you see the problem here with U77? Yeah, that chip is in backwards. So I probably just killed that IC, but let's swap it around. You know, it might be working, who knows? Funny is that when I installed this bank of RAM, I thought I paid attention to the orientation of the chips. Clearly not. All right, RAM diagnostics, round 2. If you're noticing some shimmer on the picture here, don't worry about that. That is just the RGB to HDMI not being perfectly synchronized to this CGA card. I just haven't gone in there and adjusted it. Now, some ICs, when you put them in backwards, like EPROMs, immediately die. Immediate death. But RAM, it can be pretty resilient. Yeah, it's fine now. That actually is fine. That chip survived. This whole motherboard is a survivor. It was left for dead in that PC 5160 that I got, and it just continues to work, except for the fact that this ROM chip decided to give up the ghost. And there we have it, everyone. Everything has passed. In fact, it's funny because the floppy drive was failing to read before, even though the card that's in here is the original floppy controller from this machine. Maybe it was relying on some BIOS routine that was failing because of that other chip that was bad. I mean, everything is passing now. This computer is totally working. So because I know people complain about it, I'm gonna put a little sticker over this EPROM here, so it will not get erased or whatever. 5160 U19. And let's take this diagnostic ROM out, which I'm going to erase. I won't keep that. Put the original chip back in here for U18. Turn on the machine, make sure that it works as it should. There it is, counting up the RAM. Look at that. When I wasn't paying attention, I think it got to 256K. Let's run check disk to see how much free memory there is. There it is, 256K of total memory. And there we have it. One fully functional IBM 5160 motherboard where the only fault was this failed ROM chip. So it gets the big old X on there. And with that, I hope people found this diagnostic video interesting. Talk about going down the wrong path over and over again. I was totally off on tangents, thinking that things were wrong with parts of this board that had no fault at all. Honestly, that's kind of how diagnostics go. When you're not making a video about it, you're going off on different tangents, constantly trying to figure out where the fault is, unless you're so experienced at repairs that you're able to zero in on exactly what the problem was. I've never worked on or tried to repair a 5160 motherboard other than broken tantalums, which I'm pretty sure this has that, because it looks like one of the tantalums here is missing. I think originally this thing had a shorted tantalum and I just broke it off the board. Maybe I should replace that. It's just kind of how it goes when you're doing repair work, especially on things that you're not really familiar with. Of course, most people don't make videos while they're doing repair work, so you don't really see any of those tangents. You might just see what the end result of the problem was. But when you're working on something that you've never worked on before, like this board with me, bring up the schematics and just start studying how things work. And then watch out for the red herrings, like the bus stuff I saw here with those middle voltages, which was really just a floating bus. As you do more repairs, you start to gain more experience and you'll know to look for those things and you'll be able to rule them out very quickly. With me, even though you've seen me do repairs on this channel, I still am quite the novice. And it takes me a little bit of time to think through what I'm looking at before I realize what's actually going on. Case in point was that bus problem there. So the repair of this motherboard all came down to that really useful diagnostic ROM. Otherwise, I might have gone off on some other tangents trying to figure out what was wrong with this board. Although, the fact that these were in sockets, even if I didn't have a diagnostic ROM, I could have at least done a compare feature on the MiniPro to both of these ROM chips, and hopefully I would have figured out that that other chip was bad. It's also kind of interesting, if you go back to the original video about this, that the machine was just working normally on the bench. I wasn't even touching it when this chip failed. And when it did, the computer crashed and then never worked again. So it's funny how failure modes like that can just happen. And I've definitely had that kind of thing happen with stuff that was put away in anti-static bags in boxes, where it works when I put it away and I take it out and it's now broken in some way. So I have the dead parts bin here. Let's pop this open. Pretty full of ICs there. This IBM ROM. Oh, it didn't want to go in. There it is, it's in there now. It's in its final resting place. So that's definitely it for this video. If you enjoyed it, I'd appreciate a thumbs up, but if you didn't, you know what to do. Hit that subscribe button if you haven't already. Comments down below. Big thanks to my patrons. Their names are scrolling up the side of the screen. Really appreciate the support. If you want to become a patron yourself, you can do so at the link in the description below. Check out my second channel as well if you haven't. Lots of videos over there, including the one where I think I showed this. Although maybe this was on the main channel. No, I think it was on the second channel. It's been going for a little while now. It's got like 28,000 subs or something like that. Slowly creeping up. It's just really good. So that's it. So stay healthy, stay safe. I'll see you next time. Bye-bye.